Now, okay.
Okay. I hope I'm both audible and visible.
Yeah.
Okay. So, hello everyone. I'm Ihanshu Rane. I'm a PhD student at Antarctic Research Center at Victoria University of Wellington, New Zealand. So today I'll be presenting the development of my PhD proposal, which is predicting coastal polynyas in Antarctica from regional topography and large-scale atmospheric circulations. So first, I'll quickly start by talking about what is polynya. So the term polynya is defined by WMO as any non-linear shaped area of open water enclosed by ice on all sides. Polynyas can range from 10 to 100,000 square kilometers in size, with typical alongshore length of 100 to 500 kilometers. And depending on where they are formed, they are classified as coastal polynyas or mid-sea polynyas. So these are visual satellite images of polynyas in Antarctica. This is the modernized polynya, which is a mid-sea polynya. A reference scale of 150 kilometers is given below, and we can see the coastline of Antarctic. So the polynya is formed more than 500 kilometers away from the coast. And in this image, we can see three coastal polynyas, the Terranova Bay polynya, McMurdo Sound polynya, and the Ross Sea polynya. A reference scale of 50 kilometers is given below, and we can see the varying sizes polynyas can have. So for this work, we will be focusing only on coastal polynyas. So formation of coastal polynyas. The main factor in formation of coastal polynyas are katabatic winds, which are downslope winds. So due to very low temperatures in Antarctic, cold and dense air forms over high elevation regions. So this image shows the average surface temperature in Antarctic during austral summer and austral winter, overlaid with surface wind vectors. So the dense cold air masses will flow down the steep valleys due to gravitational acceleration. And due to the orography, these are channeled into narrow sections where they converge and increase in speed. So these regions where these katabatic winds converge are called as confluence zones, and we can see them in many coastal regions in Antarctica. For example, the Ameri Ice Shelf, Ross Ice Shelf, Terranova Bay. So these high-speed winds will drive the sea ice away, forming an opening in the ocean. And at the same time, phrasal ice will form in this region, and the high-speed winds will drive it away, thus sustaining that coastal polynya. So the intensity of katabatic winds will affect the polynya size. Now, studies have shown that synoptic processes slightly affect the local wind direction, but they strongly modulate the wind speed. So this image shows some major frequently occurring coastal polynyas in Antarctic. So the 13 regions shown here are regions where coastal polynyas are seen regularly. The color scale below shows the frequency of occurrence of these coastal polynyas. So what is the importance of coastal polynyas? Polynyas drive the lower limb of global thermohaline circulation. So when the ocean surface cools, new sea ice forms, which releases brine in the ocean. So this water mass becomes denser than the ambient water and sinks. So this dense shelf water, called high salinity shelf water, eventually contributes to the formation of Antarctic bottom water. This dense shelf water also transports oxygen and other nutrients to the deeper layers of the ocean. And these coastal polynyas are regions with very high heat fluxes. So Haid and Timmerman 2013 found that if we compare the heat flux to atmosphere, inside polynyas, it is 7 to 9 times higher than the heat flux in adjacent ice-covered areas. So the motivation for this project is that global Earth system models have limitations in representing polynya-associated processes due to their coarse resolution. Now, Earth system models typically run at coarser resolutions, such as 1 degree by 1 degree, around 100 kilometers by 100 kilometers, with some modern versions running at 1/4 degree. So, firstly, the katabatic winds, which are the major driver of coastal polynyas, simulating these local high-speed winds on spatial scales will require high resolution numerical models, which can resolve the atmospheric dynamics on spatial scales of regional orography, such as valleys and outlet glaciers, for example, around 5 kilometers. Uh, Secondly, the smaller polynyas with intense sea ice production are not represented. So coastal polynyas such as Terra Nova Bay polynya, which are smaller than the model resolution, are not represented properly. This leads to large biases in salt flux, which in turn leads to suppression of formation of high salinity shelf water and subsequently Antarctic bottom water in Earth system models. Another problem is the simulation of phrasal ice formation. Since this process happens on very small scale, sub-millimeter scale, it currently cannot be simulated in models beyond lab size domain. So, however, achieving such high resolution in global models is computationally expensive. So, what is the objective of our project? The objective of a project is we propose a parameterization method that will remove the need to resolve fine-scale regional weather. So we want to predict coastal polynyas from large-scale atmospheric circulations, which are currently resolved in global models, and topographical features. So when we say topographical features, we are categorizing two types of topographical features. First, the orography, which converges and channels the high-speed winds. Second, the orientation of coast, which blocks the advection of sea ice by winds and ocean currents. So for this, we will train a machine learning model with local wind data, topographical features, and other variables, which I will introduce later. So when we say prediction of polynyas, what do we mean by that? So prediction of polynyas can be split into two sub-problems. First is the prediction of occurrence of polynya, which is a binary classification problem. That is, a polynya will occur or not for the given conditions. Second is the prediction of polynya size, which is a regression problem. That is, if a polynya is occurring, then what will be the size? Now, how is the polynya size defined? So most of the current studies define polynya size from sea ice concentration. So different studies use different thresholds depending on their requirement. For example, if sea ice concentration is less than or equal to 75%, it will be considered as polynya. However, this method provides only information about the open area of ocean, but not about the formation of dense shelf water. So more suitable method for defining polynyas to get the salt flux production information is using sea ice production. So Tamura 2008 pioneered the mapping of sea ice production in coastal polynyas based on heat flux calculations from satellite data. This method assumes all heat loss at the surface is used for sea ice formation. So next, for this project, the machine learning algorithm we will be using for predictions is random forest, which is a supervised machine learning algorithm, and we will be using for both classification and regression tasks. So in machine learning, hyperparameters are parameters that control the learning process of machine learning algorithm. So one main advantage of using this random forest is that it produces good results without too much hyperparameter tuning. So that is why we have selected this algorithm. And in this, the random forest classifier will be used for prediction of polynya occurrence, and random forest regressor will be used for prediction of polynya size. Now we were looking for existing studies correlating topography with coastal polynyas in Antarctica. And the only study we came across was Jiang 2020. So Jiang 2020 analyzed the correlation between coastal polynyas and bed elevation. Now, one small point here is that the topography here refers to the local seabed elevation. So the study hypothesizes that a combination of steep slope in bed topography and abrupt changes in wind speeds are preferential locations for generation of new polynyas. So this image shows vertical profile of local seabed along the meridional section for 6 polynya regions in Antarctica. The blue line represents bed elevation, while the orange line represents sea ice concentration. So plot A depicts a mid-sea polynya region, while B to F are coastal polynya regions. So we'll focus on these 5 ones. In plot B and C, we can see that the polynyas are formed exactly above the steep slope, while in D and E, they are formed just before the seabed slope becomes steep. So for convenience in this plot, we'll refer to the two edges of polynyas as land edge and ocean edge. So the study remarked that since coastal polynyas are distributed along the edge of ice sheet, there is a slight deviation between the land edge of polynyas in D and E compared to ones in B and C. The study also implies that the ocean edge of polynyas is still consistent with the contours of the beginning of the continental shelf slope. However, in figure F, we can see that the location of coastal polynya is far from that steep slope, which is in contrast to this hypothesis. So topography, that is bed elevation, is an important factor, but not a fundamental factor for prediction of polynyas. So now the variables required for training the model are as follows. First is the sea ice concentration. It can be classified as local sea ice and far field sea ice, where far field sea ice is the sea ice coming into the polynya from other regions. So while local sea ice will be used to define the polynya, and far field sea ice will be used in later stages to understand its impact on coastal polynyas. So the data source for the sea ice concentration is Erafiri analysis, which has temporal coverage from 1942 to the present day. Next is the sea ice production data, which we will be using for defining the polynya. So for this, initially we will be using data from Tamura 2016, which has a temporal coverage of 92 to 2013. And later we will be replacing it with state-of-the-art dataset derived from improved classification techniques between cloud-covered areas and ice. So the other variables which will be required are surface winds, speed and direction, surface air temperature, sea surface temperature, pressure, and these will also be taken from Erafiri analysis. Next is the gradient wind, which is an extension of geostrophic wind, that is wind assumed to move along parallel isobars. So it accounts for influence of both pressure gradient force and centrifugal force in mountainous areas. So it will also be used in the final stages to understand the impact of large-scale circulations. Next is the coastal orientation. It is required to understand how the shape of the coast impacts the growth of polynya. So we are still finalizing on how we will quantify it. Right now, we are planning to categorize the coast of the training regions according to just basic shapes and determine their orientation from it. I would be happy to hear if anyone has any thoughts on it or has already worked on it. Lastly, for the orography, to determine the valleys channeling these winds, surface elevation variable from Bed Machine Antarctica version 3 can be used. So now that we know the variables required, let's look at how the model will be developed. So the overall project will be divided into 3 stages. In first stage, we will be using surface wind speed, surface wind direction, and coastal orientation. And the outcome from this stage will be to better understand how the coastal orientation, that is the shape of the coast, impacts coastal polynyas. In second stage, we will be using surface air temperature, sea surface temperature, and far-field sea ice. And the outcome from this stage will be to understand the impact of temperature and far-field sea ice on coastal polynyas. In the third stage, we will be using pressure, gradient winds, and surface elevation. And the outcome from this is to understand the impact of orography on local high-speed winds and eventually coastal polynyas. So for each stage, we will be doing model training in two separate parts. Part one is by using sea ice concentration. This will give us information on just the open area of coastal polynya. So we can predict the occurrence and size of just the open area. With part two is by using sea ice production. So this will give us information on the intense sea ice production area of coastal polynyas. So we can predict the occurrence and size of sea ice production areas. An example of model training for stage one is as follows. So the input variables, which are stage one variables and either sea ice concentration or sea ice production, will be given to both the classifier and regressor. So the output of random forest classifier will just give us the prediction of occurrence of polynyas. Then this output will be given as an additional input to the regressor. So that way, only if a polynya is occurring, then the regressor will give us prediction of size of polynya. So the next step we will be doing is generating the training data. Since ERA5 doesn't capture katabatic events properly, first we will improve the ERA5 wind speeds with AWS ground truth data. So this is just a comparison of wind speeds obtained from ERA5 and automatic weather station AM02. So figure A shows the monthly climatological mean, while figure B shows the 3-hourly wind speeds for 8th August 2005, depicting a katabatic event. So we can see in the climatological mean that ERA5 underestimates wind speed by 2 to 3 meters per second. However, during the katabatic event, it highly underestimates the wind speeds by 6 to 7 meters per second. And these high speed winds are needed to form the coastal polynyas. So the first step is wind speed from ERA5 will be improved with wind speeds from AWS. For this, we will be using the AWS dataset, which has a compilation of 267 AWS data. So this image shows the location of all the 267 AWS data compiled in this dataset. Now for training the model, we have selected these 7 regions. So this image shows the sea ice production for these regions overlaid with surface wind vectors. And these are climatological means averaged over the months April, May, June. So we can see here that these regions have frequently occurring polynyas with intense sea ice production. And these regions are mainly selected due to the availability of AWS data in these regions. So finally, what will be the features of the end product which we are making? So once
Ihanshu,
the
you are having
yeah,
2 more minutes.
this is
Okay.
yeah.
Yeah.
So once the algorithm is fully trained after the 3 stages, we can give input variables from global Earth system models with coarse resolution, like global Earth system models. Then the algorithm will predict if a polynya will occur or not. If it is occurring, then the size of that polynya and the intensity of sea ice production. So this will result in reduction of salt flux biases and ultimately improve the representation of high salinity shelf water in these global Earth system models. So that is all from me. I would be happy to hear any comments or any suggestions. If anyone has worked with any machine learning models, I would appreciate any different suggestions, different approaches, if anyone has. So thank you.
Thank you very much. Is there any question for Ihanshu? Yeah, Alex, please.
Yeah, thanks, Ihanshu. It's a really nice talk, and I think it's a really important and potentially cheap way to improve ESMs because it doesn't require increasing the resolution. So that's really cool. I just put in the chat, we have a link. I put a link into a paper that we published on coastal orientation. So
Okay.
maybe that could be useful for you. And I just wanted
Yeah.
to ask you, so especially in the Cape Darnley polynya, the first one of your 7, but also in a lot of other polynyas as well, the polynya size is controlled by fast ice, land fast ice.
Yeah.
So yeah, I've got a student looking at simulating fast ice in models, but I think there's really no way of parameterizing that right now. So that might be a challenging area for you. Thanks.
Okay. Yeah, I'll definitely check this paper also because we actually needed suggestion on how to proceed ahead with this. So thank you very much for that.
Thank you.
Thank you. Is there any other questions?
I just have a naive question. I mean, it's certainly the I'm not going to go into the technicalities of using machine learning and all of that. What would cause a polynya to form in the middle of the ice? I just can't imagine what the process was that would cause that.
So in the coastal polynyas, these are mainly due to the katabatic winds. However, the mid-sea polynyas, they can be due to various reasons. So from the ocean, the mid-sea polynya which I showed, that is a modernized polynya. So there is a sea mount because of which there is a lot of upwelling, warm water upwelling in that region. So the temperature of the water is kept more than the freezing temperature. That's why the polynya is sustained. Plus, if there is any cyclonic activity near, that will also cause ice divergence and cause the polynya to open up.
And I guess how important to this program to your study is machine learning? I mean, there must be other ways to characterize this.
Yes,
and
there might be, but with normal numerical models, they have to be run on a very high resolution, and that is computationally expensive. That's why in Earth system models, it is not getting represented properly. So that is why we are trying to develop it so that these processes can be represented in Earth system models.
But then there must be other people working on, there must be these kind of problems must just occur everywhere in these Earth system models. I mean, you get minor effects that can't be resolved.
Yeah.
And is this approach being used in other areas?
Not that I know of. So we are mainly considering the topography. Like that is the highlight of our project, that the shape of the coast and the orography, which will modulate the wind speed, this local wind speeds. So that so far I haven't seen literature with this particular topographical feature considered.
Yeah.
Just
Sorry.
quickly, John.
Yeah.
Ihanshu is working with me. So there are, I'm not an expert, there are people who are working on atmospheric parameterizations to get around resolve these things. And you're absolutely, Michael, there's lots of processes that are not visible in global climate system models. And I'm sure a lot of people are working with ML to address these things. So, but we haven't done much research. We really focus polynya stuff, and there isn't actually too much out. So, big Alex, thanks for the heads with those papers.
Yeah.
Any other question or comments? No. So thank you, Ihanshu, for your talk. You can
Thank you very much.
stop your screen sharing. Thank you.